Welcome to this video on diodes. So I'm going to give you a bit of an introduction to them and then just talk about the construction of a simple diode. You can see from this slide here we've got a circuit symbol for a diode on the right, and you can see it's got a cathode and an anode. N-type and P-type should become a bit clearer later on, but basically all that means is the type of semiconductor material that the cathode and the anode are made out of. So in simple terms, a diode can be thought of like a valve in terms of hydraulics. A valve will allow fluid to flow in one direction, but it won't allow it to go back in the opposite direction. So a diode is exactly the same, but for electrons. So electrons can flow through one way, but they'll be blocked from going the other way. From there, we'll just do a little bit of a recap on our semiconductors, conductors, and insulators. In terms of construction of these, the atomic level construction, we can see down at the bottom that we've got an atom there, and in the center we have our nucleus. So the nucleus is where the protons and neutrons are located. Protons obviously having that positive charge, neutrons having a neutral charge, and then you can see the red ones around the outside are the electrons. The electrons actually orbit around the nucleus. The electrons themselves are located in shells, and the outer shell is what we call the valence shell. The amount of electrons we have in that valence shell determines what type of material the component is. If there's 1 to 3, then we class it as a conductor, 4 class it as a semiconductor, and from 5 to 8 it becomes an insulator. You can see from there that the higher the number, the less inclined the material is to conduct, and that's basically because it has a full, or very close to having a full, outer valence shell, and so therefore is less inclined to give out those electrons. And obviously, going back to our electrical theory, we know that current flow is the flow of electrons. So those ones that have 1 to 3, they're actually trying to get rid of those electrons, or they find it very easy to let them move out of the orbit. So there we go, there's our conductors there, and here you can see it says it has 1 valence electron, but they can have up to 3 as well. Next one is our insulators, and they're bound very tightly, so hard for them to give up electrons or take any electrons in as well. And semiconductors, which is obviously the basis of this whole topic, the ones we're going to be talking about have 4 electrons in the valence shell. So the 2 most common types of our semiconductor material are silicon and germanium. And you can also see carbon is another example as well. But in terms of diodes, silicon and germanium are the 2 main materials we use. There's also a word that comes up on that second sentence on there where it says about intrinsic. So a semiconductor that it's in its pure or intrinsic state is neither a good conductor nor a good insulator. So it's between the 2. The reason that intrinsic is important because later on there's a technique that we use to make our semiconductors more useful, and therefore we have to add different elements to them, and they are no longer pure. So we can see here this is a comparison between a semiconductor and a conductor, and if you look at that valence shell, you can see the one on the left, which is our silicon atom, has 4 valence electrons, whereas our copper atom only has 1. So less tightly bound, easier for that electron to break from its orbit. Comparison between the 2 main types of semiconductor, silicon and germanium. You can see that both have the same amount of electrons in the valence shell. The difference is, though, germanium has more inner rings, so it has more of those shells in there. So the valence electrons are actually further away from the nucleus. As they're further away, they've got less of the electric force holding them together. So between the protons and the electrons, there's less force holding those electrons in, so it's actually easier for them to break out of that orbit. So you'll find germanium is less used because of that fact, because any sort of temperature variations, germanium can become unstable. So not as stable as our silicon throughout temperature ranges. Covalent bond, this is what happens with our silicon atoms because they have the 4 electrons in the outer shell. So what silicon does, it forms this thing called a covalent bond, which is like a crystallized structure where it shares an electron with each of the atoms that are surrounding it. So you can see the inner silicon atom in there. We've got 4 silicon atoms around the outside, and they're sharing one of each of those. So it actually gives the effect that silicon atom has a full outer valence shell and therefore 8 electrons. This makes it very stable in normal situations, so no impurities. It has a very stable state. Okay, electron hole pairs. So what we mean by an electron hole pair is this is basically any sort of temperature variation will cause some of these electrons in the valence shells to actually have enough energy to move out into the conducting band. So they can break from that orbit. As they break, they leave an object called a hole. So a hole is actually, it's not anything, but the lack of electron being in that atom now causes an imbalance between electrons and protons, and therefore it actually has the effect of having a positive charge. So those electrons break out of that orbit, they'll wander around, and then they'll go into another hole. So they'll join a hole from another atom. And this is just basically a random scattering of these electron hole pairs throughout the silicon material. So this is where we get onto the main construction of our diodes. You can see at the top it says N-type and P-type. So in order to make our diode, we have to construct 2 different types of semiconductor material. We do that by adding other elements to our silicon. So we call this process doping, and it's where we add additional elements into our silicon material and therefore change the atomic structure of the material. So the first one we look at is N-type. Looking at the diagram there, you can see that we've got silicon atoms and we've got another atom on the inside, and the symbol for it is Sb, which is antimony. So antimony is a material that has 5 valence electrons. So it actually has 1 additional electron compared to our silicon atom. By doping this with our silicon atoms, and you can see the covalent bond that's formed, we now have an electron that has no position in the outer ring. So we now form a material that has 3 electrons. We call this type of material, this antimony, we call it a pentavalent atom. Penta, obviously coming from 5, like a pentagon. So this material, antimony, similar materials are arsenic, phosphorus, and bismuth. They all have those 5 valence electrons. By doing this, we've now created a material that has electrons that are free in there, floating around. Reason that we call it N-type comes from negative, because of the extra electrons that are in that material. However, important part is that this material isn't negatively charged. So a common misconception is because of these free electrons that the material becomes negatively charged. However, there is still the same number of protons and electrons throughout the entirety of that material. So it is actually of a neutral charge. With regard to our N-type and P-type, we talk about majority and minority carriers. So this is how our current flows. Due to the abundance of our free electrons, the majority current carriers in our N-type material are electrons. We still have a few of those electron hole pairs. So remember those thermally generated atoms that broke free out of the orbit and then left a hole and moved into another hole. We still have some of those, so we call those our minority current carrier. P-type material, exactly the same process as making our N-type. We use another atom to dope and change the characteristics of our silicon atom or silicon material. In this case, however, we don't use a pentavalent material, we use trivalent impurities. So trivalent impurities, some examples are boron, indium and gallium. Trivalent, obviously from tri, meaning 3, they have 3 valence electrons in the outer shells. So by doping those in, now no longer do we have a full complement in our valence shells, we actually have only 7 electrons. So with this in mind, we've effectively got a hole that's left in those covalent bonds. From there, we can see that they're often referred to as acceptor atoms because they have these free holes that electrons are able to flow into. Majority current carriers in our P-type material are the electron holes, and the minority carriers are our electrons that are created through those electron hole pairs. So with those 2 materials, what we can now do is actually join them together. By getting our N-type and our P-type material, we sandwich them together, and we actually have a scenario where we have electrons that are free from our n-type material are now attracted over into the holes of our p-type material. So you can see from the picture down below, those free electrons that weren't able to find a place in the valence shell are now able to flow over, and they're able to reside in those holes. However, if we remember back to what I was saying about the charges on our n-type and p-type material, because they both had an equal number of electrons and protons, they were both in their normal state neutrally charged. However, now that the electrons have left a region of the n-type material and moved into the holes in the p-type material, we've now got an imbalance of electrons and protons. So if you look at the n-type material on that side where those electrons have left, it now has effectively become positive because there are more protons than electrons. Whereas on the p-type material on that same side, we've now got an abundance of electrons, and that gives us a negative charge. So we've effectively created a potential between those two regions. This area is what we call the depletion region, and it's the whole basis behind the operation of our diode. From here, once these electrons have moved over and residing in the holes that were left in the p-type material, they'll get a point where the electrons on the n-type material no longer see the force of those holes or the attractiveness of those holes because of the large negative potential on that p-type side of the depletion region. And therefore it creates a state of equilibrium where we've got this range in the middle that has a negative and a positive charge, and no longer can electrons flow over. Another name for this depletion region is our barrier potential, and that relates to the value of charge between those two parts of the p-type material and the n-type. Because of the obvious imbalance of electrons and protons, we have this potential here, and that potential is actually a standard. So for silicon, that value will always be around the 0.7 volts, whereas for germanium, it will be around the 0.3 volts.